Thank you very much for attending this session. I am Ardavan Asef-Vaziri from California State University, Norwich. United States, after China, of course with a big gap, is ranked second in terms of waterborne container handling. Combined ports of Los Angeles and Long Beach are 10th among all ports in the world regarding waterborne container handling. 1/3 of waterborne containers pass through ports of Los Angeles and Long Beach, which are also recognized as San Pedro Bay ports. The value of the trade passing these ports is about 8% of the value of trades in goods. About 250,000 firms consider ports of Los Angeles and Long Beach as their inbound hub or outbound hub. Out of 10 jobs in Southern California, one is associated with San Pedro Bay Port activities. We have learned that if teaching material are linked to real-life applications, they improve the student physical, mental, and collaborative presence in the learning process. I had about 31,000 records on origin-destination data for ports of Los Angeles and Long Beach, each with about 10 fields, and I tried to build a little bit of story around them for a class of business analytics foundations. What makes Port of Los Angeles and Long Beach attractive is water depths of about 60 feet, around 70 miles of waterfront, 6,000 acre area, 50% land, 50% water, 14 container terminals, and around 150 ship-to-shore containers. But more important than these two are two characteristics of all forecasting techniques. These are the routes from East Asia to United States. The shortest one is to San Pedro Bay ports. So forecast for near future, forecast less into future is more accurate. Therefore, forecast for 2 weeks from now is more accurate than forecast for 3 or 4 weeks from now. Furthermore, majority of these shipments are for the whole United States, not just for California. And because aggregate forecast is more accurate than individual forecast, this has become a competitive edge for San Pedro Bay Port. So we from Far East, they forecast for a near future, shorter time into the future, and then for aggregate data, which in general shows less variability. This case study was partially implemented in a class of an undergraduate class of business analysis foundations. So we played a little bit with aggregate data to forecast for the future 5 years from now and 5, 6, 7 years into future. The first curve is inbound loaded containers. The second one is outbound empty containers. The third one is outbound loaded, and the last one is inbound empty, and we have done forecasting for a few years into the future. Actually, we had about 31,000 record. We cleaned them up. We dropped about 30% of them, and that led to, say, for each zip code, we had about 48 shipments, 143 TUs, and about 920 tons of car goods. The average tonnage per TU was about 6.4, and the number of TUs per shipment was around 3 in this clean data. This is a picture, so the student take the Excel sheet and prepare a graph like this using Excel maps. About 47% of containers are delivered by truck, and around 53 of them are delivered by trucks. And that leads to heavy congestion at port gates and also at freeways close to the port. The idea here is to, instead of directly send the containers to the final destination, we send them first to an inland port and then deliver them from the inland port. An inland port is located away from the seaport. Railroads links the inland port to the port. Clean air locomotives or maglev systems do the transportation. Among other benefits, inland ports in Southern California can increase the capacity of the ports, create smoother flow on congested freeways, and increase transportation efficiency by switching from truck to train. With respect to distribution of the origin destinations from Port of Los Angeles and Long Beach, we identified those origin and destinations in 5 counties in Southern California. It was about 407 zip codes, and 80% of the container was delivered to 50 zip codes, and 98% of the containers were delivered to 200 zip codes. Regarding the distance, 80% of the load was within 40 miles of San Pedro Bay ports, and 98% was within 80 miles. This is a pictorial distribution of the destinations. This 407 zip codes in Southern California, in 5 counties in Southern California, were origin and destination of about close to 1 million TUs. The weighted distance between this origin and destinations and port was about 27 miles. We assume 300 days per year and 1.8 TUs per shipment per truck. That leads to 6,000 TUs, 6 million TUs per year for 2030, which is translated into about 11,000 trips per day and around around 300,000 vehicle miles per travel per day. We developed a single facility location for this data, and we identified a location about 7 miles to the south of downtown Los Angeles and to the west of Freeway 710 to be a good point for an inland port. These are the existing facilities in Southern California, and the location that we found is around this place. Under these circumstances, the original distance, weighted distance of around 27.8, 75% is translated into 15.9 miles from inland port to origin destinations, around 3.6 miles from port to this, and a weighted average of 19 point at a total of 19.5. So this 27.8 is reduced to 19.5. But at the same time, we do have 13.7 miles from seaport to inland port. But a train can replace 150 trucks, but we may reduce that 13.7 because a train can replace 150 trucks, and fuel efficiency of a clean air locomotive is something at least four times of trucks. This is the distribution of the destination between inland port and the port. And these are contour lines to show if there was not a suitable parcel of land in the optimal location of inland port, how much the vehicle mile travel increases if we move to other locations. We prepared this by using mathematical equations, but we prepared this just by using, which delivers the same knowledge, mainly by using Excel data tables. And this one by Excel maps, which delivers the same knowledge. To make it possible to solve a problem in Excel and to have a nice graph of the region, we decided to aggregate the data from 407 to 100, then to 75, 50, 25, and 12. And we use this version of 25 aggregated nodes for Excel implementation of single facility location problem. We created a background of the to a scale of the area, and also provided the optimal solution based on the center of gravity, and also based on the actual optimal solution, which is the minimization of the square root of the summation of square root of distances. And as you know, these two do not coincide. We also build an Excel page to examine the rectilinear distance optimal solution, so a student can change these numbers and play with this tool a little bit. We then developed a model for the location allocation problem to identify the location of 1, 2, 3, 4, 5 inland ports. One component in the objective function is cost of inland ports. One is transportation cost by truck from inland port to final destinations, and one component is transportation cost by train from seaport to inland port. To make it possible in Excel, because Excel do not handle more than 200 variables, we reduced the size of the problem to 12. We aggregated 407 nodes into 12 nodes. And this is if we only have the inland port, the seaport. This is if you want to create one inland port, two inland ports, three inland ports, and 4 and 5 inland ports. Because it is difficult to find a large parcel of land in Southern California to be able to handle around 3 million TEUs per year. So we cannot have conventional storage system. We thought about having something like a storage and retrieval to be able to manage this volume of activity. We are thinking of inland ports to handle 1 million TEUs per year. And that's it. Thank you very much for attending this session.